next slide, please. Thank you. So now moving on to the flexure or the spring design. So we'll start here with the low profile. That's kind of the bread and butter of interface, right? It's a web shear design. Let me pull up my notes real quick. So you can see there's a lot going on with a low profile, an LP. It's an assembly design, so typically, right, it's got the flexure as well as the base, and there's a lot that goes into it. So we want to balance quite a few parameters to make sure that we got the best performing load cell. So you see there the beam height and the beam thickness. That's basically going to control the stress at your gauges or the strain at your gauges. And that's very important because not only does it control the relationship between force and strain, it also determines how the strain is kind of flowing through the flexure. So remember before how we talked about the strains need to be aligned with the grid lines. If your beam is maybe a little bit too short or a little bit too thick, you can see how you'd start to get more bending than true shear. And so the strains wouldn't be aligned with your grid lines anymore, and you start having performance issues. We want to concentrate the stresses at the gauge. That's really important for performance. It also is just good design, and you're going to avoid a lot of stress concentrations that way. Except you can see on the beam height there, we have that little notch that kind of is acting as a stress concentration to make sure that the gauge is seeing the most stress. That also helps in what Brian's going to talk about a little bit later, which is the moment compensation. That gives us kind of a nice radius to mechanically moment our load cells. A few of the assembly aspects that are important when it comes to an LP, since this is going to be bolted to something, right? Hopefully a base, but if you're doing it on your end, it's going to be bolted to hopefully a hard flat surface. And the flat surface is pretty important. So you see the loading rings on the right. Those are used to keep the contact surfaces flat and also perpendicular to the applied force. And that's really important because you can kind of imagine if the load cell wasn't sitting quite flat and you were applying a load perpendicular to a flat surface, you would not be applying that in the, you'd have off-axis loading is what would happen. Another thing too, the bolts, we typically have, about one bolt per beam, and that's important, right? Because the bolts are basically acting as what's keeping the dead end truly dead. And so the bolts have to really torque down and hold the assembly so that the live end is the only part that's moving.
Hey, real quick, I want to highlight something too.
Yeah.
If anybody's spent any time on our data sheets or has used a lot of our low profiles, you'll know we offer different capacities all within the same form factor, right? So we'll have a 1210, a 1220, a 1232, or vice versa for the series. And what we're doing there is we're varying the beam dimensions within the same package, or maybe even varying the beam counts. Maybe we cut some of the beams out. So it allows us to have a little more manufacturing flexibility, but then also be able to standardize more on the customer end in terms of integrating with different sensor types or different capacities, excuse me. So obviously we reach a certain point where we have to grow that the diameter, and then we fit another range of capacities within that, and that's all through changing the internal dimensions there of the beams. So
Good point. Thank you, Brian. Alrighty, so now we're going on to the LBMU. And this is a load button. And load buttons, as Brian kind of mentioned before, get a bad rap. They have their pros and their cons. Load buttons, they don't transfer moments to the beam, right? There's no, fixed point of load application, which doesn't transfer moments, but it also can cause some linearity issues if you're applying the force in a different location than what was intended. And that makes these load cells very, very, very sensitive to gauge placement. So you can kind of see some rough dimensions here. This is a really small load cell, right? It's, I think, smaller than a quarter, maybe smaller than a penny. It's pretty small. And you can think about trying to install 4 separate gauges in very specific spots repeatably. And that's going to be really hard to manufacture. It's going to be really hard to have good, consistent performance. So since Interface makes our own strain gauges, we were able to make an all-in-one. This is also called a patch gauge, and this means that the tension and compression gauges relative to each other are in the same location every single time, and the technician only has to install one patch. So this helps these load cells perform as best they can, and also be a cost-effective cell to manufacture. Alrighty, so next slide here. Now we got the MRTP. So this is interface proprietary. We got a patent on it by LeVar and Mr. Burrow there. And next slide, please. This one is measuring torsion, torque, and it is overload protected. So you can see there that kind of blue highlighted surface. That is attached to a column that's going down the middle, and it has those arms that kind of go out with those EDM slots. And those EDM slots are overload gaps. So the load cell is allowed to deform a certain amount, and then it contacts those surfaces and can't deform anymore, and it's overload protected. So this is really important for low capacity load cells because they're very easy to overload, right? Even handling it or installing it, torquing down some bolts for to apply the load, you could very easily overload it. So this is a really, really good design, and you can see the raised surfaces there too. That's what helps keep the live end, the load application of that outer ring, from touching the dead end overload stop column. And another beneficial aspect of this is the beams are on the outside, so they're very easy to access for gauging and wiring. Alrighty, Brian.
All right. So multi-axis and flexure consideration. So here's two different options to accomplish the same thing in terms of offering a sensor that will do FZ and XY shear. The one on the left, you can imagine, was one big spiral there. So those are essentially three bending beam sensors bolted together. You can actually see the little gauge potting there that covers where the gauges are with the white areas. So you can imagine that they all kind of tie together. So it works. There might be some compromises in terms of deflection, stiffness, as well as maybe introducing a little bit higher crosstalk, right? Because every single element there is going to respond to that force. So that's one way to do an FZXY shear, is to have them all connected. The one on the right there has a center section that's bolted in to discretely measure the vertical, and then it interacts with two different sections beneath it to then be able to transfer the X and Y. So it's just a different approach there, whether they're all in one or isolated as much as possible from a multi-axis standpoint. Next slide. So here's an example of our 6-axis sensors. These are obviously full axial as well as bending moment solutions. These are a little bit unique in that instead of having a discrete output where each channel gives you specifically an FX value or an MY value, there are 6 or in some cases 12 millivolt per volt channels coming out. And the reason for that is internally there's various beams that's pretty representative there in this drawing here of what it looks like. Often called a Stewart platform or a hexapod, but each one of those beams will have strain gauges on it, will have a bridge on it. But it's not necessarily designed that each one of those beams is going to measure and provide the output for those different axes you're looking for, right? So instead you get a composite output with everything, and through calibration and characterization of the sensor, and then typically through calibration matrix adjustment on the instrumentation side, which is why we always recommend one of our BX8 amplifiers with these units, so you don't have to do the math yourself. You can then isolate and calculate out what the discrete outputs are for each channel or each axis, excuse me, that you're trying to measure. So here's an example of, again, a multi-axis where instead of having a bridge that is specific to the axis of measurement, you have many different millivolt per volt signals coming out, but through very careful and accurate calibration, you can characterize how a specific applied load impacts each one of those millivolt per volt signals, and then be able to run that into your instrumentation. All right, next. So load pins. Load pins are typically hollow pins, so center of the flexure will be drilled out. The flexure design is going to be a function of the application dimensions typically. Most load pins sold are custom, right, in terms of either the diameter or the length or where the loading surfaces are for that setup. But the key takeaway there is they come in two flavors. They're going to come in either an internally gauged solution or an externally gauged load pin. And the externally gauged are going to have much bigger exposed pockets. They usually have to be potted or in some cases like welds. But Interface primarily offers internally bonded solutions for load pin, much more rugged. We can seal off the ends of the load pin and protect the gauge cavity. So, but the important thing to note here is that the flexures are very sensitive to how they're loaded. So on the left there, is a good depiction of what we would recommend for good performance. We don't want to bend a load pin. We want to keep it in double shear. So that means that the reaction surfaces, as depicted by those outer two elements, want to be tightly controlling not only the diameter aspect, but also the interface to the middle loading section. So as you push or pull that middle section up or down, you want to make sure that the stress concentration areas depicted by the grooves. Again, if you reflect back to some of those other flexures where we neck down the material so that we can maximize strain. Same thing going on here. The gauges are going to be directly under those grooves, but that's where you want to have that double shear interface occurring from a system level standpoint. So it's really important you have tight tolerance, that you keep the pins in shear, and that you don't bend the load pins. So, all right. Next. Sealing.
Alrighty.
Back to you, Jake.
Alrighty. So sealing considerations, right? This is directly related to the application and the environment the load cell is going to be used in. You can see there in the middle, we have a welded, kind of hermetically sealed 3200. And so we got the welded diaphragm. That's going to be top and bottom, as well as a welded, we call them a dog house, where we put a lot of the tabs and perhaps an amplifier. And then we have a cable gland coming out here with the cable. You see here on the left, SSM, that stands for like a sealed S-style load cell. And it basically has a cable gland on one side, and then that internal cavity where we have the strain gauges, we kind of backfill that with a gel potting compound, and that helps seal the bridge from any moisture ingression. Then, on the other side, the right side there, the MB, that's pretty much exposed. So it still has a gauge overcoat, a conformal coating that we put on almost all of our load cells. But besides that, the wires and stuff like that are only protected by the that cover. So if you put, a screwdriver or something in there, you could ruin the load cell. And it really depends on the application, right? So we have some load cells that are being used, in oil drilling applications with 20,000 psi of oil around it. And then on the other side, we have load cells that are being used in high vacuum environments where everything needs to be vented and outgassing is a concern. So really working with the applications engineer on your unique environment and use case is really important in getting a load cell that's going to be good for you. Next slide, please. All right, and so we'll talk about flexure material types real quick. Obviously, the one of the main things to consider here is the strength of the material and the capacity that you're trying to measure. So you're going to see we use 2024 aluminum. It's low strength, but it's good performing, very low hysteresis material. However, it is limited to around 300 degrees because that's when the aluminum starts to temper again. Then if we look over at 4340 steel, this is super common, very easy to machine, low hysteresis, and it's very, very strong. So we use that for most of our LP range. Then if you're looking for corrosion resistance, it doesn't really get better than 17.4. It's very corrosion resistant. It has very high strength, but it has worse hysteresis than a 4340. So there's always going to be the drawbacks and the weighing the pros and cons. And there's all sorts of other materials you could use, right? Titanium is one that's used for highly corrosive environments and maybe very hot situations where you still want an accurate reading. The obvious drawbacks there is that it's very expensive, very difficult to machine, and so it's very, very rare.